So in order to help us show that the rational numbers are countably infinite, we're going to introduce a new theorem. It's called the Cantor-Bernstein Theorem, okay? And it has two parts. The first says that if the cardinality of A is less than or equal to the cardinality of B, and the cardinality of B is less than or equal to the cardinality of A, it tells us that A and B have the same cardinality. And we've seen this idea before, also reflected in the fact that if A is a subset of B and B is a subset of A, then the sets A and B are the same. Okay, and we've seen this in the homework, we've seen this in previous lectures. The second part says if there exists an injection from A to B and an injection from B to A, then there exists a bijection A to B. Okay? And so we'll use these two pieces in showing that the rational numbers are indeed countably infinite. Okay? But sort of as an aside, this sort of implies that if the cardinality of A is less than the cardinality of B, there has to be an injection from A to B. And let's just show a little example of why that might be true. Let's just suppose we have some finite set A1, A2, A3, and B, whose cardinality is bigger. So let's just say we have B1, B2, B3, and B4. If B has more elements than A, we can always find an injection from A to B, right? And this is talking strictly in the finite sense, right? We can always find an injection because there's no need to overlap, because if there's more elements in B, we can always just draw an arrow from each element in A to some element in B without having an overlap, just as we've done here. Since there's only 3 elements in A and 4 elements in B, we don't need to overlap 2 elements in the output, okay? And that's sort of a consequence of this theorem. And so we'll extend that to sets of infinite size. So now what our job is to do is we need to do 2 things. We need to find an injection from the natural numbers to the rationals, and an injection from the rationals to the naturals. Okay? And one, I guess, question is, why are we doing all of this as opposed to just trying to find a bijection directly? And the reason is, it's because it's much easier to find 2 separate injections in this case than it is to construct a bijection, okay? Since the rationals are indeed countably infinite, a bijection does exist by definition, but it's much easier to prove this statement in the way that we're going about doing it now. Okay? So first, let's establish the injection between the naturals and the rationals, okay? And the only condition we need for an injection is that it doesn't map 2 elements in the natural numbers to the same rational number, okay? And it's fairly easy to find this injection. It just maps element x to x, right? This makes sense because any integer can be written as itself divided by 1, indeed, which is a rational number. So this will not map any 2 natural numbers to the same rational number, right? If A and B are 2 different natural numbers, their outputs, A and B, will just be different rational numbers, okay? So this is indeed an injection. Now our second task is to find an injection from the rationals to the naturals, okay? And this is slightly more difficult. And to help us with this, we'll take a look at this diagram, okay? And in future courses, you might hear this being called the spiral diagram or the snake diagram. And essentially what it is it's finding an ordering of the rational numbers, okay? And we have inputs being the rational numbers and outputs being the natural numbers, okay? You may say here, well, where are the rational numbers? All we have is some grid of ordered pairs. But it turns out we can almost think of the rational numbers as being a Cartesian product of the integers, right? A Cartesian product of the integers would look like the set P comma Q, where P and Q are integers. While the rationals look very similar. It's P divided by Q, where P and Q are integers. And of course, in both, we have that Q is not 0. Okay? So what we will do is use this similarity and just use an ordered pair system, a Cartesian system, to convert between ordered pairs and rational numbers, okay? So what we will do is treat coordinate a comma b on this grid as being the rational number b over a. We could also use a over b. It doesn't really matter. I'll use b over a just because it allows us to look at the slope of a point. Okay? And what we need is in the left column to have every rational number at some point. Right? In order for it to be a function, it must map everything in the domain to something in the codomain, right? So we need to have every single rational number in the left column. Will that be a problem? No, because the way this pattern sort of carries itself about is that it will eventually reach every single ordered pair, right? If we continue this further and further, any ordered pair a comma b you give me, no matter how large, it will eventually reach it, okay? So eventually the rational number b over a will be hit. Now, what we need to do is account for the fact that rational numbers will appear multiple times in this sort of snake pattern, right? The point 1 comma 1 maps to the number 1, but so does the point 2 comma 2, right? In fact, any number on the line y is equal to x will map to the point 1, except for 0 comma 0, which we will arbitrarily set as being the number 0, okay? And how do we account for this? Well, we only look at the first occurrence of each natural number. So only look at first occurrence of each rational number. Okay, so that means when we get to the point 1 comma 1, we write down 1, but then when we get to 2 comma 2, we don't write down 1 again. Okay, so as an example of what this injection would look like formally, so our natural numbers are 1, 2, 3, 4, 5, 6, and 7, so on and so forth. The first number we look at is 0. The next number we look at is 0 over 1, which is again 0. So we don't need to include that. The next point is 1 over 1. We don't have that yet, so we include it. Anything on the y-axis is invalid because it's y over 0. Those are not valid rational numbers. The next point we look at has an x value of -1, y value of 1. So that's 1 over -1, which is -1. We don't have that in our list yet, so we'll include it. So we have these points so far accounted for. Anything on the x-axis we've already seen as it's equal to 0. The next point we have is -1 over -1, which is equal to 1. We've already seen that. Y-axis, we don't count that. The next point we've already seen because it's -1 over 1, which is already been accounted for. Now we finally have reached a new point, right? This says x value of 2, y value of -1, which corresponds to -1/2. We haven't seen that, so we'll include it. X-axis we've seen. This point up here has x value of 2, y value of 1. Okay? So that means it corresponds to the rational number 1 over 2. We'll include it and continue. And we do this so on and so forth until we eventually have a pattern that will reach any rational number that I want. Is this function an injection? Yes, because no two rational numbers are at the same position on the spiral, right? No two rational numbers are at the same position. Right? Because there's only one point at every point, effectively, right? So each rational number, if we're only counting the first time we see it, is at its own unique point. This function is indeed an injection. Okay? So we found an injection from the naturals to the rationals. We found an injection from the rationals to the naturals. This implies that there's a bijection between these two sets, implying that their cardinalities are equal, implying that the rationals are countably infinite. And that is a proof that the rational numbers are countably infinite. Okay? This spiral path gives us an ordering of when each rational number is hit. Okay, so we've shown an injection from rationals to the naturals. Here we showed an injection from the naturals to the rationals. We've shown both directions. So we have that there's a bijection between the two sets, and therefore the rational numbers are countably infinite. The last set of numbers we're going to look at is the set of real numbers. Okay, so the real numbers, which usually when we're talking about functions is usually what our domain and codomain are, denoted by this fancy R, is the set of all possible distances from 0 on a number line. So this is a fancy way of looking at this definition, but suppose we have a number line extended infinitely long in both directions. The real numbers are all possible distances from 0. Okay? And this definition is a little abstract, but a real number is essentially anything that was a rational number plus numbers that cannot be written as rational numbers. Okay? And that's where the irrational numbers come in. Okay? So the irrational numbers are denoted by R minus Q. So it's the difference of reals and rationals are the set of all real numbers that cannot be written as an integer divided by an integer, right? And so examples of these are pi, negative e, square root of 5, so on and so forth. There are no integers a and b such that these can be written as a over b, okay? So there's no solution to this, okay? Whereas in real numbers, some of them are rational, some of them are irrational, okay? And this goes without saying, but we have the ordering naturals, whole numbers, integers, rationals, reals. Okay? And notice the irrational numbers are not a superset of the past four sets we've seen. The irrational numbers do not contain the integers or the rationals or the counting numbers or the whole numbers. Okay? So we have the real numbers and the irrational numbers. The question is, are the real numbers countably infinite? Okay? Again, they're dense in that in between any two real numbers, there's an infinitely large set of real numbers in between them, just like for the rationals, right? So if a and b are real, there's infinitely many numbers in this interval. So they're dense as well. But the rational numbers were dense and they were countably infinite. But it turns out the real numbers are uncountably infinite. Okay? The proof of that is sort of out of the scope of this course. But we can refer you to future courses in discrete math that sort of go over this idea and go over this proof. If you're interested in researching it, it's called Cantor's diagonalization. And it proves that there's no ordering of the real numbers. Okay, so there's no ordering of the real numbers. There's no bijection from the naturals to the reals. Okay? So to recap all of the sets we've gone over the naturals, which were our basis for countably infinite numbers, gone over the whole numbers, which were essentially the naturals with the 0 tacked on, went over the integers, which extend this set slightly by adding the negatives of all of the whole numbers. We then have the rational numbers, which are integers divided by integers. We then have the reals. Okay, and somewhere in here, not as a superset of the rationals, we have the set of irrational numbers. Okay, and a better look at this is given in this diagram. Okay, naturals, whole numbers, integers, and rational numbers, each of which is a superset of the previous sets. And then we have the irrational numbers, which are completely separate from any of these four sets, and the real numbers, which are consisted of rational numbers and irrational numbers, right? So every real number is either rational or irrational. And this diagram does a good job of describing that. Okay? And so one question is, where do complex numbers come into play? Okay? And so we've decided not to formally cover complex numbers directly in this course, but they're in the appendix. of the textbook. Okay, so if you refer to the appendix, it sort of extends this discussion, redefines what complex numbers are, looks at some properties of them, and then extends this diagram to include complex numbers as well. But if you're interested, real numbers are a subset of the complex numbers. Okay, so you can draw a box around this entire thing and write complex as well. And that caps off our discussion on the sets of numbers that we're interested in.